Good morning, everyone, and welcome to our training academy. As usual, any questions, please put into the chat and we'll address those after the presentation. In the meantime, I hand over to Denny Walensky, HRC's Managing Director, to do introductions.
Good morning, everybody. Welcome. Our presenter, Duncan, has chosen Honey Badger Bootcamp as the charity today. Let me just tell you a little bit about them. In South Africa, many teenagers face daunting odds raised in single-parent families or foster care. They grapple with exposure to gang life and drugs. Their dreams are stifled and their prospects seem bleak. Honey Badger camps aim to set them on a new path away from temptation within the community. Through participation in the Honey Badger camps, teenagers learn more about themselves, their limits, new skills, enabling them to be more responsible for their own life and make better decisions. Together, we can keep teenagers off the streets and provide them with transformation experiences. Your sponsorship will positively impact the lives of teenagers, developing essential skills and preventing them from falling into the grasp of gangs. We will put it in the chat, and if you've got a few extra R100 or whatever, please, we would really help these children to grow. A very big thank you to Marius Atterbury of the Fire Protection Association. He has introduced us to Duncan. Duncan Boyes is the chairman of the Centre Group. He started off as a teacher, majoring in physics. He later went on to gain tertiary education in marketing management. This was followed by a diploma in financial management and later a certificate in fire engineering. However, a passion for business led him away from teaching to undertake several business ventures before ending up in the fire industry. Duncan has spent 37 years in the portable fire extinguisher industry, primarily on the manufacturing side. During this time, he's been the chairman of the Centre Group for the past 33 years and has chaired the SAQA Fire and chaired the SABS Standard and Technical Wording Committees, including being representing SABS at international standards. So we welcome Duncan, and his presentation is amazing because we had it last week because this one was oversubscribed. So welcome back, Duncan. And just by the way, this is a 2-hour CPD session, and Bev will be sending you your certificates. Any questions, just pop them in the chat. Over to you, Duncan.
Denley, hi. Can you hear me? Is it all okay on that side?
Yes, we can.
Okay. Yeah, very, very, very interesting, everybody. Thanks very much for such a fantastic participation. This is the first of a second presentation, although very interestingly, the second presentation took place last week. So it seems that things are sort of quite upside down in the world, and our presentations are going backwards as well. Last week, I did have a little bit of difficulty. Some people are more technically challenged than others, just on sharing the screen. So I think what I should do and what would be prudent is if I share my screen now and then carry on. So let me start by getting the screen shared. Can everybody see that?
It's all good. Thanks, Duncan.
Absolutely fantastic work first time, isn't it? I just thought it would be a little bit prudent to give everybody a very brief overview of the Centre Group and what we do. The group was established 33 years ago. The nature of our business is covered by our byline, and our byline being complete fire protection. We have established it as a franchise, and today there are over 30 franchisees in South Africa, Sub-Saharan Africa, and the Indian Ocean Islands. We deliver on our byline, that complete fire protection, through 5 divisions, and those are portable fire extinguishers. Here we focus on your hose reels, your portable trolley units, and all the little bits and pieces that go with fire extinguishers. But I think the main thing here and the main takeaway is that Centre is the only manufacturer of portable fire extinguishers in sub-Saharan Africa. The second division is our electronic fire detection and gaseous suppression division. Linked in with that, we also supply and install kitchen systems. Then we have a division that handles automatic fire sprinkler supply. The Centre Group are the distributors of reliable automatic sprinklers. Our fourth division handles exports. Our exports are primarily focused around Africa, sub-Saharan Africa for that. And then our fifth division is a national maintenance division where we focus on maintenance of fire protection equipment. This division, they have developed an app which is linked to a barcode, which gives our customers 24/7 viewing of their equipment and the status of their equipment. So with that out of the way, I can move on then to our lithium ion presentation. The question, and I just want to check the moving on of the slides. There we go. That will move on this way. The question that comes to mind, and sorry, just going back to it, I've called it a 101 presentation. We go to bookshops and there's always the 101 for dummies. I know that we're not dealing with dummies, so I left that part out. But it really is a 101 overview. It's an overview for people who don't feel that they know a lot about lithium and lithium fires. And it's an explanation taking you through all of that. So the question is, are lithium battery fires a real concern? And absolutely. Pretty much everything that surrounds us today has a battery in it, and you'll find that those batteries are lithium-ion batteries. And we're going to talk around this and where they come from. But today's presentation, I would like to view as more of a journey of facts, where we explore a number of aspects. And what we're going to go through today, we're going to look at the makeup of a lithium-ion battery. We're going to look at the chemistry of lithium, how it's sourced, looking at its chemical properties, and it's all kept low key. So it's not going into highfalutin ways of looking at it. Then we'll get to understand the phenomenon of thermal runaway. It's a phenomenon that is bandied around a lot, but I have discovered most people who use the term don't actually know what it means. Then we'll get into the actual fires themselves, where we'll get to understand how they can be extinguished, if they can be extinguished. We'll look at three main categories of lithium-ion fires. This is something that I've developed. I don't think you'll find any research looking at calling the fires and terming them into categories, but you'll understand when we get there why I've categorized them and how relevant they will be to you and to your everyday work. We'll look at test requirements and methods of testing. We'll look at portable fire extinguishers themselves. Containment of fires has become a huge thing around the world, so we're going to touch on that. And then we'll end up by looking at risks and finish off with developing an action plan or setting out an action plan. Now, because there's so much information to be covered, I have kept the slides as simple as possible. I don't like slides with a ton of writing all over them. I'd rather talk through what is on the screen. And you're most probably going to find that I'm going to repeat myself quite a lot as we go through the session. Much about lithium and lithium battery fires is just very confusing to all of us. And because of this, I'm going to trust that by the end of this presentation, you are a lot more unconfused than what possibly you are at the moment. So let's start off by having a look at the actual makeup of a battery. Going back in time, we've experienced, starting from the left-hand side, lead acid batteries. Those morphed into gel batteries, and today we have the lithium battery. And they all look very, very similar. The lead acid, unfortunately, back then, one had to put distilled water into it, and after a time, it would give up, and one would take it out of the car, wherever it was, and get rid of it. The gel, don't use distilled water anymore, and now we've got the lithium-ion battery. And if you look at those, the housings are all pretty similar. In fact, if you took the markings off, you might not know whether it's an actual gel battery or a lithium battery. But we'll come back to that housing later, because it's quite interesting that they all are in some form of housing. But now let's look at the actual lithium battery itself and see how very different it is from the lead acid and the gel battery. Your lithium battery is made up of a multitude of tiny little cells. You can see the picture on the left-hand side, looking like little penlight batteries, all stacked together, put inside that housing that we saw on the previous slide. Now, they're made up just like any normal battery would be. There's a cathode, there's an anode. The cathode is your positive side of a battery. Your anode is the negative side of a battery. In between the two, there is always a separator. The separator is just there to prevent the cathode and the anode from coming together. If they happen to come together, it would just create a short, and that would be the end of the battery. It wouldn't work. It wouldn't do anything. And then all of that is surrounded by electrolytes. And we're going to come back and have a careful look at those electrolytes, because it's electrolytes that are causing the real problem inside there. Now, interestingly, when I speak to people about lithium batteries, they tend to believe that the battery is actually a big chunk of lithium, and it has terminals on it. That's not the case at all. The amount of lithium in a cell, one of those little cells you can see with the green parts on it, is actually pretty minimal. The lithium in this instance, the diagram that we've got showing the cathode, it will have a minute amount of lithium, but the minute amount of lithium can still cause a lot of trouble for people. So with that in mind, let's move forward and have a look at why it can cause trouble and how it can cause trouble. I do have a little statement there that says an ion is an atom or a molecule with a net electrical charge. That side is very interesting to know as well, because we are talking about lithium-ion batteries versus a lithium battery. There is a standard lithium battery. Now, a lithium-ion, just remember the name ion, because we're going to come back to that, and I'll explain to you in a short while exactly why it is a lithium-ion battery and not just a lithium battery. So, for the meantime, let's move on. Let's have a look at how lithium is actually obtained. That's going to take us through the chemistry of lithium and lithium ions. So, how is lithium obtained? This is most probably a presentation or a little extract here of useless information, but I think you're going to find it incredibly interesting information. Lithium is mined through three methods. The first method is known as the brine-based extraction. The second, hard rock mining. And the third one is direct lithium extraction, or what they term DLE. So let's go back to the first one, and now it starts getting interesting. All right, brine. Brine is that water that's mixed with other elements, and in this instance, it's mixed with lithium as well, but it's deep underground, and it's extracted from underground. It's then spread out into pans, almost identical to salt pans, and the water evaporates off the brine. The brine is left behind. It's sort of a whitey color. It almost looks like salt, actually. A whitey color. That then goes through a massive process. Now the interesting part, brine extraction. To make a ton of lithium, you can use up to 2.2 million liters of water. Now, a lot of these plants and extraction bases are found in Chile. Very much like the picture that we're looking at. It's very arid, it's very desert-like, lack of water. The water for farming comes from an underground source. This is, remembering, it's a green product that we're talking about. Is it a green product? I'll leave that up to you. We're taking that water out from the underground source. We're putting it on the surface. We're allowing it to evaporate. We can't use it again because it's gone into the atmosphere. The problem is that the farmer who's trying to get his crops to grow, particularly in an area like Chile, is finding out that he is running out of water to grow those crops. Big problem. Hard rock mining. That exactly as it says. Rocks are taken with lithium, a metal in it. They crushed. They are then water's added to it. And in this instance, with hard rock mining, most probably about 2,000 liters of water is used to produce about a kilogram of lithium. The difference, though, between hard rock and brine mining is that the water that is used does not need to be evaporated, so it can be reused, redirected as well. Then the last one is direct lithium extraction. That is most probably the best method. The lithium is extracted out of the brine, not via evaporation. Most probably only 400 liters of water are required here to produce a kilogram of lithium, but that water is recyclable. So that's a little bit of useless, interesting information about lithium and how we get it, because everybody tells you one needs to use a lithium battery because it is environmentally friendly. Interesting. The chemistry of lithium. All right, here we have things that we do know about lithium. It's a soft, silvery white metal. It heads group 1 on the periodic table. You don't need to worry about that. What is quite important to know is that it's an alkali metal. And an alkali metal is a chemical that can dissolve in water. It's a chemical that can combine with acids to form salts, and it can also be added to acids to make acids less acidic. And alkali metals, which you will be familiar with, are sodium and potassium, for example. Now, lithium only has 1 electron on its outer shell. You will see in the middle of that screen, there's a little square and it says Li, that's sign for lithium. And there's a big 3 in the top left-hand corner. That 3 is the atomic number. And the atomic number tells one how many electrons, how many protons there are in an atom. And in the instance of lithium, there are 3 protons. And if there are 3 protons on all atoms, they will be matched out by electrons. Now, electrons are what you can see on the very right-hand picture with the blue lines. and the electrons buzz around the protons. The protons are always positively charged, and the electrons are negatively charged. Because they equal out, they create a static charge, a neutral charge for that atom. Now, if I take that would be, as you're seeing it, that is a lithium atom. Pretty stable as it is. What makes it unstable is the fact that it's only got 3 electrons. So it's right at the beginning of your periodic table. You can go up to the end of the periodic table where the elements that have like 118 electrons buzzing around. And those electrons buzzing around are sort of almost like a rugby team, I suppose. If you wanted to play against New Zealand, Springboks wanted to play, and they only had 3 players, one wouldn't be very effective. But if you have 15 players, we would do really well against them. And if some instance we could put 30 players on against their 15, we would clearly do really, really well. So the more electrons you've got, the more an atom is able to hold itself together. Now, with the instance of lithium, 2 of those electrons buzz around on an inner circuit, so they sort of pretty much together, but one is stuck there all on its own. And in most probably normal terms, that one isn't happy being on its own, and it's quite happy to duck off and go and party somewhere else, join some other atom or molecule. As soon as it does that, now you've made that atom unstable. There will still be 3 protons. They're positively charged. Now there are only 2 electrons. So that atom now has a positive charge. The 3 protons outweigh the 2 electrons. And that is what an ion is. So that's the difference between a standard atom and an ion. It's, again, some of that sort of useless information. Now, another point of useless information is that lithium reacts vigorously with water. So storing it is certainly a problem. We spoke earlier about sodium and potassium being alkali metals. The one thing about sodium and potassium, you can store them in water. You can store them in oil. Sorry, not water. You can store them in oil. And that's where they can stay. Lithium, unfortunately, you can't store in water because it reacts with oil. You can't store it in water because it's so light. You can't store it in oil because it's so light that it bobs to the top of the oil. And so storing lithium itself becomes quite a problem. So that's us taking a slightly deeper dive into the chemistry of lithium. Let's have a look and see then other things that we do know about lithium itself. So we already know that it's an alkali metal, and we know what an alkali metal is. We know it's a metal that's able to dissolve in water, although we do know that lithium dissolves vigorously. We'll look at that now. Lithium is very unstable. That little electron on the outer side, it is quite happy to go off and join somebody else. And as soon as it does that, lithium has then become unstable. It has become an ion, and now it also doesn't know quite what to do. It's extremely light. It'll float on water. When one has a lithium ion cell, it tends to very, very slowly vent. And when it vents, it mainly vents carbon dioxide. It's not carbon dioxide being vented to any high degree, so it's not actually a problem for anybody. Lithium reacts with water, as we've said, but this is where the interesting part is. It reacts with water. One of those little electrons jumps off, joins water, and it forms a hydroxide and hydrogen gas as well. And I think, as we all know, hydrogen gas is highly explosive. So that's where we have a problem then with our lithium and putting it into water. Lithium ions fires are able to generate their own oxygen when burning. Now, this clearly becomes a problem because you can't smother this fire. You can't go and take your vehicle and put it into the swimming pool, which, by the way, there are videos of this, the exact same scenario happening, because it'll carry on burning. When the lithium is heated, volatile organic compounds are discharged from that lithium ion battery. And these come from those electrolytes. Remember in that very first, or one of the first slides showing the battery, we showed the anode, the cathode, the separator, and that all of that was in the electrolytes. It's those electrolytes that are causing huge amounts of problem. And with those electrolytes, when they burn, and this happens around about 170 to 500 degrees, hydrogen fluoride is one of the hydrogens or hydroxides which are generated. The concern with hydrogen fluoride is it's absolutely deadly to man. We cannot survive it. Burning lithium creates a metal fire, and it creates a metal fire that is hotter than the average fires. Its fire, because of the nature of the electrolytes and the lithium combined together, it can rise to temperatures of about 200 degrees Celsius. Now just put that into some everyday context. An orange flame, one has a candle, the orange flame that one sees on the candle is somewhere around 1,100 to 1,200 degrees C. And then also on a candle, you'll usually see a white flame. That white flame is that much hotter. It's about 1,300 to 1,500. And then the brighter the white, so the hotter it is getting. Your lithium fire burns with a very bright white flame, and that can go anything from 1,500 to 2,000 degrees C. That's hot. That's very, very hot. Now, why are lithium battery fires so serious? Because they create what is known as a feedback loop. And in this feedback loop, those little cells that we saw in the picture of the battery, one of them starts getting hot. It gets hot to the point that it now heats up the little cell next to it, which in turn gets hot and heats up the cell next to it, at which time the first cell might have already started going into flame. That process of the cell heating up the next cell, heating up the next cell, that feedback loop process, that is what is known as thermal runaway. So with that in mind, let's move straight on. Let's have a look at this process of thermal runaway. So starting on the left-hand side, we have three little cells inside our battery. One of them is a little bit darker than the other. It's starting to heat up. Something obviously has caused abuse of it. It gets hotter, and at around about 170 degrees, as we've said, it's getting very hot, and it's also starting to release the hydrogens. So that's a gas coming off. Now, that's quite important to know, because at that point, when we get into fire detection, there are detection means that can pick up those hydrogens. So, yep, this battery is getting pretty hot already, but it hasn't got that hot, and maybe at that point there's something that we can do. We're going to find out about that a little bit later. But now, carrying on with this process of thermal runaway, the first little cell is getting very hot. It's causing the other cells around it to get hotter. Ignition then occurs in the first cell, and before you know it, ignition has taken place in all the cells that there are. Now, one thing to bear in mind here is going back to those pictures of the batteries. The battery is contained, or these cells are contained in a thing called a battery, which is a plastic housing. It might be a metal housing. I'm not aware of too many metal housing, but yeah, it might be. So this process of thermal runaway is taking place inside the confines of this housing, but we don't actually know about it. We don't know it's actually taking place. Possibly the first time we will know is right at the end, when the 3 cells are now burning and that casing has exploded open. Another little bit of useless information from this. The first cell that goes into fire. So on the very right-hand side, we can see one of the little cells is now showing it to be burning. It is not possible to put that fire out. There is currently no means to extinguish that. There are possibly means to prevent the other cells from also burning. And those are things, that's something that we're going to be having a look at next. So next, we're going to have a look at what can cause these cells to heat up. Now, when a lithium-ion cell starts heating up or goes into fire, it's usually when the battery's on charge. Or it could be if something has punctured the battery and gone further to puncture the actual cell, and some of those electrolytes are now coming out of the cell, and those electrolytes are then touching an ignition source, and that will cause an immediate fire. So when I said right at the beginning, we need to bear in mind those flammable electrolytes. The lithium does set it off, but they then go into this feedback loop, and that is the main cause of thermal runaway. So what could cause this battery of ours to overheat? There could be a spontaneous internal or an external electrical fault, just like a short circuit, possibly being punctured. That's one of the big concerns with the EVs, the electric vehicles. The batteries are on the bottom of the electric vehicles. They are fine unless they get punctured. That can be a serious problem. Overcharging a battery. Overcharging a battery can cause one of those little cells to then start heating and causing the rest to go into thermal runaway. External heating. When tests are done in batteries, usually the way that the battery is set on fire, a flame is put underneath the battery, it's heated excessively, and then the battery catches alight. So external heating or possible fire. Mechanical abuse, or it could just simply be a manufacturer's defect that we're looking at. So I think we want to go on now, and we want to have a look at extinguishing these lithium-ion fires, because that's what everybody seems to want to know. And how do I extinguish it? And we don't really worry about anything else around it. Well, before we go and do that, let's just recap where we were. So we've had a look already at how lithium is mined. We've had a look at the chemistry and a number of properties of lithium. And I think we've had a closer look at thermal runaway, and I know that we will all understand thermal runaway a lot better now, especially after that lovely little slide that I'll show. All right, so we get into extinguishing a lithium-ion fire. Well, it doesn't matter what type of fire you wish to extinguish. You're always going to go back to the age-old fire triangle. And the fire triangle tells us that a fire, which we know better as combustion, is a chemical reaction. And there are 3 elements that that prevail during that chemical reaction. There must be fuel, there must be oxygen, and there must be heat. And therefore, or thereby, you will get a chemical reaction. Now, the same way it tells us that there are 3 elements that are required, we are also aware that if we can remove one of those elements, we should be able to stop that fire. So the elements that we can remove, and in this instance, there are now 4 elements that we can remove. So we can remove the fuel, we can remove the oxygen, we can remove the heat, we cool it. So removing heat is usually done with water. Removing oxygen is usually done by smothering it somehow, putting a foam over it, putting a blanket over it, putting sand over it, whatever. And removing the fuel, physically taking the fuel away. But there's also a chemical reaction. And we can prevent that chemical reaction taking place. And I'm going to share some really useless information, which most probably all of you already know. But it's how dry chemical powder fire extinguishers work. In a dry chemical powder, the common powder that is used is monoammonium phosphate. And most people believe that the powder is simply a blanket. It's a smothering thing. There's a fire, a little bit of a wood fire in front of one. One takes a fire extinguisher, one covers it with the powder. We've put a blanket over it, end of fire. Actually, that's not how your firefighting powders work at all. Your firefighting powders react with that chemical reaction. For example, monoammonium phosphate will break down. I can explain this to you at a later time. I'm not going to go into depth now, but in essence, a free radical is formed in that breakdown. The free radical then steals an electron from this process called combustion, and it's no longer combustion. I always love sharing that useless piece of information with people, because most people believe that firefighting powders is just a white powder, or people do color their powder as well, and it's just like a blanket. It is far more important than just being a blanket. Okay, so let's have a look at extinguishing the actual lithium ion fire. So before we look at the triangle, there are a couple of things we've got to bear in mind. A lithium battery is made up of lots of small cells, or you can call them batteries if you want, and they're in a case, so you can't necessarily get to them. Lithium, when it's burning, produces its own oxygen. That's going to create another problem. And a lithium fire reacts quickly and is extremely hot. It can jump up to 1,500, 1,200 degrees C very quickly. And the reason why I've said that is, if you are fully garbed in fire protection equipment, you will move towards that battery. If you're a layman and you've got 1,500 to a 2,000 degree C fire, I don't think you're going to be that keen to move towards it. So on the lithium side, let's go back and have a look at that fire triangle. The fuel, well, the fuel's in the battery. It's part of, we can't remove it. Oxygen, not helping us at all, because it's quietly producing its own oxygen. Even if we take it and smother it, bury it, put it in a swimming pool, and all of these are YouTube clips which one can go and watch. I purposely haven't put on any clips onto this presentation. They take too long, and I think anyway most people have seen most of the clips. Then there's a chemical reaction. Nobody yet has formulated a way to upset the chemical reaction, so that's not possible. And the fourth means is heat. Well, that is the only means that we've got left. We can remove the heat. So as we've said, and going back to looking at those clips of thermal runaway, the actual active cell, there is nothing you can do to that. But if you can get to the other cells, you could put water on them, for example, and you could cool them down to a point that thermal runaway is prevented. So the active cell will carry on burning. It won't burn for very long. An example of this, if I take a cell phone and set that alight, a cell phone battery will burn for about 2.5 to a maximum of 3 minutes, then it's burnt itself out. So those little cells that were in the picture of the battery, much smaller than a cell phone battery, they would burn themselves out quicker if you can get to them fast enough. The problem is you might only discover the fire when it's too late, and that battery, the entire battery, has now caught light. Right, so we're going to use that looking at the heat method, or reducing the heat, removing the heat, whatever we can do, as our means of fighting that fire. So with the information that we've got so far, we can take a little bit of a deeper dive into the lithium fires themselves. Now, for convenience, I have broken up and divided the fires into 3 categories. And you'll understand as we go through the categories why I've chosen the 3 categories. And I think you'll find that in your line of business, those categories are very pertinent to you. The 3 categories that I've put lithium-ion batteries into, very simply, small, medium, and large. So a small category will be for a battery of 600 watt-hours or less. Now, if one takes the battery, a lithium battery that is used in an electric scooter, that size battery is most probably sitting around 600 watt-hours. And then the batteries obviously get smaller than that. Then I've looked at and separated the fire into a medium size. And the medium size, because there are many installations around, particularly where people might have used solar power to then go through an inverter, and they're using that to charge lithium-ion batteries. And they might have a cabinet, like in the picture. They might well have a room with 10 or 20 batteries inside it. Those batteries, if you add up the watt hours, will all add up to a lot more than 600 watt hours. And as I've said, I will explain to you just now why I've set on the 600 watt hours. And then we get to the large installations, the energy storage systems, or what some people prefer to call battery energy storage systems, BESS. And it's on this end that most probably the greatest concern is regarding batteries and battery fires. So we'll start off by having a look at the small lithium-ion sites. So small fires, watt hours, less than 600 watt hours. It's very, very easy for one to calculate the watt hours. Watt hours is equal to volts times amp hours. And if one has a look on any battery, you will find that stamped onto that battery are the volts of the battery and the amp hours. You simply multiply them together and you will end up with watt hours. Now, on small lithium-ion batteries, there is a fair amount of work being done on it and a fair amount of research, and it all comes around fire extinguishers. So when we have a look at the research that's done, the institutions that I've been in contact with that are doing testing on small battery fires are organizations like UL, United Laboratories. By the way, they're not doing a huge amount of research. They're putting all their research into the energy storage systems, but we'll come to that. Organizations like LPPC are doing research. There are a number of universities doing research. And then there's an organization known as Kiwa. It's a Dutch test house, and we're going to talk about them in a little bit more detail just now. But it's interesting the type of research that they're doing. They've been researching on almost all types of mediums that they can, mediums which they believe could cool down, so won't prevent the active cell from burning, but would quickly cool down the other cells around it. So they've looked at things like liquid nitrogen, looked at water mist, D-class powders, wet chemicals. Some of those wet chemicals are encapsulators, and I'll explain just now what encapsulator is. And then they also, there's a product known as AVD, aqueous vermiculite dispersion. And these are all products which research is being done on. The vermiculite one is very interesting, actually, because vermiculite is really well known in the fire industry. If one is taking a walk in the Karoo or up in the Drakensberg and one kicks the dust, one often finds like a little shiny flake, and there are a number of them. That flake is vermiculite. And where we know vermiculite from many, many years back is vermiculite forms the basis of passive fire protection. And it forms so passive fire protection, or what people can term as well intumescent paints, the paint that you paint on a wall to create a fire barrier. And it's a very good fire barrier. It has a number of interesting properties. It's a very poor conductor of heat, and it also expands when it comes in touch with heat, and that expansion obviously creates an additional protective layer. So wet or aqueous vermiculite is just that same product. It's been turned into an aqueous solution by adding it to water and other additives. And that obviously makes the dispersion a lot more functional than if it was the standard vermiculite and it was just crushed into a light powder. Being added into water, its dispersion capabilities are that much greater. All right, let's have a look at the actual testing of small fires. So currently, we need to bear in mind that there is no international standard pertaining to lithium-ion fires. We also need to bear in mind that once a fire goes into thermal runaway, it's actually pretty difficult to stop. But of all the organizations that I spoke about earlier, there is one, and it's known as Kiwa. It's a Dutch testing house, and they have been doing tests, and in fact, they've gone further than just doing the test. They have created their own internal standard, which is known as NTA 8133, and they are using this standard, and in fact, quite a number of people, organizations around the world are sending their product to the Kiwa test house to be tested. I was speaking to a Chinese company the other day who wanted to sell our organization lithium fire extinguishers, and I said, where's the medium? Do you test them with medium? And they said, yes, it is sent to Kiwa. If you talk to people in the UK, most around Europe, they will use Kiwa as their basis. It is not an international standard, but it is currently the basis and the test that is being accepted at the moment. On discussion with other test houses, it is believed that the Kiwa test, with a number of adaptations to it and alterations to it, but the Kiwa test will end up by forming the basis of the testing for fire extinguishers with a lithium-based medium in it. Now, you remember that I referred to it as small small lithium-ion battery fire. The reason why I have set on the small is because the test that Kiwa do will take one up to 600, a 600 watt hour battery. If you remember, that would be the battery about the size that would go into electric scooter. And that's as far as fire extinguishers get tested. Interestingly, during their tests, Kiwa place about 5 batteries side by side. They will heat up the battery on one end, get it to go into fire. As soon as it goes into fire, they will use the extinguishing medium that they are testing to put over the balance of the fire the first battery or cell which has actually activated will end up by burning itself off, but they are trying to prevent thermal runaway for the rest of the batteries. And then they have a test procedure. Once the flame has gone out, they wait for something like 20 minutes to make sure that thermal runaway doesn't reappear. Interestingly, though, the Newcastle University, they stack about 6 to 8 cells on top of each other. And they activate the first one. They do have a burn time. They have a minute of burn time, and then they will put the medium onto the fire extinguisher, onto the battery. When asked why they wouldn't have a pre-burn of longer than 1 minute, they stated that those 6 to 8 batteries will burn themselves out in about 8 minutes. So they would then be left with about 7 minutes to test the medium that they are using. Of the tests being done by the number of organizations who are testing, it has been shown that encapsulators and water mist were the most effective mediums to be used. And I'm just going to move that on. I'm going to explain the encapsulator side now. So fire extinguishers that are currently in our market, they range from 1 liter to 9 liters. After 9 liters, I don't think there would be any value in the product. The mediums are predominantly wet chemicals, water additives, wet vermiculite, ABD, and D-class powder. And I've added D-class powder because a lithium fire is not a true metal fire. But there are some D-class powders that have the ability to absorb heat from a fire. So those D-class powders would be suitable. Now, I know in our organization, we use a D-class powder, which is used on metal fires, traditional metal fires. But to be honest, I wouldn't have a clue whether the D-class powder that we use actually has the ability to absorb heat from a fire. I'm not even aware of such testing having been done. The question that, okay, so the wet chemicals on the market are Lithex, and I'm just naming them. I'm not promoting any product. As I said, this presentation is not a sales presentation. It's just a presentation on fact. Lithex, F500, Fireblock, Flamebock, FFX Lion, which is a lithium-free agent. I used the word encapsulator earlier on, and what is it? Encapsulator, it's exactly as the word says. It's a product that will surround another. So in this instance, we're talking about batteries, and we're talking about little cells in the batteries. So it's a product that will surround that whole cell, and the aim of that encapsulator is to prevent the heat from going from your one cell to another. Wet chemicals are a very good encapsulator. They speak for themselves. Obviously, being aqueous, being wet, they are runny. They can move around a product. They can move around a battery. Graphene, I have put it there. Graphene is an incredible encapsulator. Unfortunately, it's unbelievably expensive. It's pretty difficult to harvest. And until it becomes economically unviable, it most probably won't be used. So a question that's always thrown to me, and it's sort of quite a difficult one to answer. So they say, all right, Duncan, well then great, that's great to hear that. Which is the best fire extinguisher for me to use? And I think the answer comes from a number of questions that maybe the user needs to ask, and ask of the supplier of the fire extinguisher. The questions that I would put forward would be questions like, I would check the medium, check the stability of the medium. Has it been tested for lifelong livity? The medium of an extinguisher is what puts out the fire extinguisher, not the fire extinguisher, what puts out the fire, not the fire extinguisher. So a lot of people are selling fire extinguishers. I wouldn't worry too much about the fire extinguisher. I would be concerned about the medium inside the fire extinguisher. I'd also be concerned about how the medium discharges. Tests point to a spray type discharge being the preferred discharge. I'm not saying that it has to be a spray. I'm just saying that it is currently the preferred method of discharging. I would have a look at the medium as well and see if it's certified. Has it been tested and approved by Kiwa, for example? I would also have a look at discharge distances. It's amazing. I was sent a video the other day by a Chinese company wanting to sell us lithium fire extinguishers, and they had a video of a person putting out a lithium battery fire. The discharge from the extinguisher was most probably a maximum of 1 meter, and by the time the person had ended up extinguishing the fire, extinguishing the battery fire, they were standing right over the battery. It's all very well if you kit it up with fire protection garb, but I don't think that we can expect a layman to do something like that. So it certainly would depend on let's see a video on your product and how close can I get to that product to extinguish it. And then most probably the last thing that I would look at there, and these are just suggestions. I'm not saying that this is the be all and end all of it. And in fact, all of it you can most probably take and scrap if one so desires. I would look at the medium to see whether it's an encapsulator. So, for example, I mentioned a D-class powder. A D-class powder clearly isn't an encapsulator. It might go on top of the battery, but what's happening to the sides and the bottom? One would like to know that the product can flow all around the battery, and certainly if the battery bursts open, that it can flow in and around the little cells that are inside there. So I would have a look at that encapsulation part, and is the medium able to flow or isn't it? Okay, when we have a look then at containment of small lithium-ion battery fires, there are a number of things that we should look at. First of all, just practical storage. We've learned already that if that battery goes into fire, most probably it's going to be too late to get to it, so it's going to be burning. So decide where you want to store it. And my suggestion would be, don't put your battery in the lounge, and also don't have it in the garage where your car is. I would have a little area, preferably built out of brick, outside the house, and that's where I would prefer to store my lithium-ion battery. So if anything happened and they did burn, they would eventually burn themselves out. There would be massive explosions, and it would be quite a horrific scene. But one's house would be fine, wouldn't burn down, and one's garage and car and what have you wouldn't burn down. And those seem to be the two places where everybody wants to store lithium-ion batteries. Fire blankets are useful. I'm going to come back to fire blankets when we talk about the medium-sized fires. There's something very interesting there that's just come to our attention. But the fire blanket, if a fire blanket's going to be used, it needs to be a fire blanket that's tested at least up to 1,500 degrees plus that, if you can find one. Because remember, your lithium-ion fire will burn very, very hot. A normal fire blanket is used for anything from 1,000 to 1,200 degrees. So a normal fire blanket would just burn through. Fire extinguishers, but we've already gone through that, are used for containment of small lithium-ion battery fires. And then just sound housekeeping. Be very careful what is around the battery. Is there anything that is flammable that could produce a secondary fire? Because I think that's most probably the biggest problem with the lithium-ion battery fires is actually the secondary fire. So I've put a question there which just says, what is the purpose of a portable fire extinguisher in lithium-ion battery fires? Now, it's very interesting to note that NFPA don't promote the use of portable fire extinguishers. End of story. That's their decision. The one thing with your fire extinguisher, which we have already mentioned when ascertaining what would be the best fire extinguisher, is to look at that discharge distance, because will it give you enough distance to be able to stand away from the fire and try and extinguish it, or do you have to be right on top of the fire? Because if you have to be right on top of a fire, you're not going to find too many lay people who would get anywhere near a lithium-ion battery fire. And by the way, if you've seen a picture of a lithium-ion battery burning, those little cells, once the battery itself bursts open, those little cells start flying around, and it is a horrifically scary experience. So what's the purpose of these fire extinguishers? And the bottom line is there a purpose? Well, personally, I believe, yes, that there is a purpose. If you have an ability to possibly contain a fire, I would rather know I had that ability than I had just decided not to have anything like NFPA ever said. They just say, let it burn. The concern is, for me, not so much the lithium battery, because I'm not sure I can do much about that. But my concern would be the secondary fires. And that's why I would also like to know that the product that I would use would be very aqueous, would be a wet chemical. Because if that battery bursts open and one of those little cells shoots across the room and hits a curtain, and the curtain starts burning, does the medium that I have inside my fire extinguisher, does it have the ability of putting that fire out as well? In other words, is the spray wide enough? Is it far enough? Is it aqueous enough to do that? So, for example, if my curtain started burning and I had a D-class powder, I'm not sure that that's going to be that helpful for me. So yes, I do believe that extinguishers certainly have value. Right. I think that's enough about the small class of fires. Let's have a look at the medium class now. Here we have a picture. We have a number of batteries inside a cabinet. I've just made up a haphazard example of fires, so of battery sizes. So I've said here we've got 5 batteries, they're 12 volts. They've got 100 amp hours in them. Therefore, their watt hours combined would come to about 6,000 watt hours. Clearly, fire extinguisher is now out. Fire extinguisher will be useful up to 600 watt hours. And the reason why I'm saying this is because I'm reading about institutions that are adamant that you will put a fire extinguisher next to such an installation. And I think the only question that possibly needs to be answered is why would you put it there, and what would its purpose be? And if that can be answered, then I would go ahead with if the answer was feasible enough. Unfortunately, very little research is being done on these medium-sized fires. So there is a little bit of research being done on the small, and there is research being done on the energy storage systems, but there's not a lot of research being done on this medium-sized lithium-ion battery fire. So really what it comes down to is the containment side of it. What do we need to do? What can we do to try and contain a fire? And what has been proposed up to now are the use of fire blankets, aerosol units. I am told have been tested and are effective inside a cabinet. Gas detection, and the gas detection would most probably be used more in order to remove the battery if you knew which one was overheating, or the use of fireproof cabinets. Now, the first part that I've got there is fire blankets, and something that's very, very new to us now, literally 4 weeks old, are the tests that the NFPA have been doing in the study that they've been doing on fire blankets, particularly in covering EVs, electric vehicles. What they have discovered is that there is a massive buildup of your VOC gases, your volatile organic compound gases, underneath that fire blanket. And that, at a point, leads to a phenomenon known as deflagration. And deflagration is a form of combustion where a flame propagates at subsonic speeds. The response from NFPA: do not cover your EV with the fire blanket. Those people wanting to know a little bit more about deflagration, it's very similar, and it's a cousin actually of flashover. So if you have a room burning, there's always heavy black smoke that rises to the top of the ceiling. That heavy black smoke is filled with heavy particles, and at a point they get so hot that they literally explode. And that phenomenon is known as flashover. Deflagration is very similar to that. So from the 4 original solutions of containment for a medium-sized fire, it seems that fire blankets should be removed. I'm not saying that they have to be removed. I'm simply giving you the feedback of the NFPA studies. All right, this takes us then to the large fire, and the large fires being in ESS or energy storage systems. There is a reasonable amount of work being done in this, primarily along the UL/NFPA side of things. So if I have a look at the research that they've got, most of it currently is working on separation and container separation. So NFPA and UL have 3 papers out at the moment. They are not current standards. They are papers. They are still being researched. You could refer to them, I suppose, as reasonable suggestions. And they are on the screen at the moment, UL 1973 or UL 9540, or you can look at NFPA 855, and those are all papers on separation. Now, some of the information that are contained in those papers is they are stating that containers should be separated by at least 1 meter apart. Then within the container, and they talk about horizontal or vertical, there should be a 2-hour fire rating. So what they would be looking at is saying, have a set number of batteries together, let's say 8 batteries, then you would have a space, and in that space alone can be a 2-hour fire separation. It doesn't necessarily have to be a blanket, a brick wall, or something like that. So the space must be far enough that if those 8 batteries go into fire, they're not going to heat up the batteries that are whatever that distance is away, 2-hour fire rating distance, and cause them to go into thermal runaway. So they talk about horizontal and vertical. They don't state exactly how it has to be done. I can understand the horizontal side. I'm not sure how one would do the vertical side, but if one looks at most energy storage systems, they tend to today just have one layer of batteries. Now, I know when I first started getting involved in lithium ion fires and batteries, there were people, particularly in this country, who were buying containers, 6-meter container, and then just filling them full of batteries. They were horizontally next to each other. They were vertically on top of each other, with very little space to move. And I think that's what the NFPA are trying to say. That is a no-no. They've also restricted the size of the containers. So they look at an enclosure and they say that it shall not exceed 6.2 by 2.6 by 2.9 meters. That's pretty much the size of your standard container. Then on top of the separation, on these storage containers, one looks at detection, removal and containment, and extinguishment. So let's have a look at each one of those. On the fire detection side, what is available, what it could be useful? There are temperature probes that are available. So a probe goes onto each battery. It goes back to a control panel. Should one of those batteries start heating up, and obviously that temperature is set with the probes and the panel, should the battery start heating up, somebody can move in and remove that battery from the container. There are gas detectors. We've spoken about the hydroxides. They will pick up the hydroxides. One can use that to possibly go in to remove the active battery that's overheating. There are aspirators as well. Aspirators, breathing, sampling the air. They would also work on sampling the gases. And then there are thermal cameras. And of all of those appliances, my personal favorite would be the thermal camera. And the reason why I would go for the thermal cameras above anything else is that, first of all, the thermal camera is giving you a visual of the inside of the container and all the batteries. Secondly, it is highlighting the actual battery which has become active. So if you're in a guardhouse or control room, you can dispatch somebody to that container, and they can go directly to the battery. With the other means, you might be able to go to the battery, to the container, but you most probably won't be able to know exactly which battery is heating up. And if it has gone into thermal runaway, well, then you don't want to be in the container anyway. You need to get out. There are suppression systems. I understand that Siemens have a suppression system. They use the aspirator to detect the gas output, and then they're using nitrogen as a suppressant. I'm not 100% sure what their methodology is. There are automatic sprinklers, and I know that the company that we represent, Reliable, have developed now a sprinkler head which has been UL approved for lithium ion batteries and batteries in large storage areas. And then there are water mist systems. And from the feedback that I received from Newcastle University, water mist systems and encapsulators are the two best means of extinguishing a lithium-ion battery fire. And it goes back to your fire extinguishers. So a fire extinguisher, you can have an encapsulator, an aqueous medium inside a fire extinguisher. But I don't think water mist would work too well with a fire extinguisher. You wouldn't be able to get enough water to come out, because water mist, once it's activated, it keeps going. And that's just the feedback from Newcastle University. Water mist and encapsulators are the two best scenarios. But at the end of the day, whatever scenario one is looking at, one has to also take into account the removal and containment. And if one looks at a battery manufacturing factory, they have thermal cameras, and the batteries are coming along a belt. And if there's a battery there that is at a temperature that is not what they've approved to, they simply take the battery off that line, slide it into a containment area, it goes off, and if it's going to burn, it'll carry on burning. They don't try to do anything else with that battery. They leave it be and let it burn. All right, we're coming right to the end of our presentation now. The last two things I said we would look at would be the risks associated with the fire, and then our recommended action plan. So let's have a look at the risks. And initially, there was only one risk. There was a primary risk, and that was the risk of fire. There's now a risk that has become almost greater than the risk of fire, and that's the risk of the gases, those VOCs, or volatile organic compound gases, that are discharged during a lithium battery fire. And research shows that a 1 kilowatt battery can produce between 500 and 1,000 liters of gas. That's a lot of gas going into a room. So if one has a room with batteries in it, one of the batteries has gone off, and somebody's told to go in there to remove it, or whatever they ask to do, the recommendation today is the secondary risk is far too great. You've got the discharge. One of those volatile organic compounds is hydrogen fluoride, and you will not last, literally, you will not last 3 seconds in breathing in hydrogen fluoride. So the secondary risk of lithium-ion battery fires has become and has moved right to the forefront. So with that, one has a look at internationally action plans or recommended action plans that are developed. And one notices the action plans don't include running in to try and either remove the battery or throw water on it or use a fire extinguisher or anything. emergency, and it's suggested that all organizations create an emergency response plan, not just for their staff, but also for firefighters. And those emergency plan or an action plan should include fire alarms. So in the active area, in the area where the lithium batteries are kept, there should be fire alarms. Those alarms will activate to a main panel, which will help evacuate people from a building. A means of escape, a full-on escape route needs to be developed so that people can move away if there is a lithium-ion battery as quickly as possible. At the same time, there needs to be access for firefighters. It's no point having one's lithium batteries right at the back of a set of offices where nobody can get to. So cognizance needs to be taken of that. Then cognizance needs to be taken for the provision of water. In other words, fire hydrants, are they close by? Then really important, because of the VOC gases, is the venting and smoke extraction. So it's great to have a room which is now filled with batteries, but has venting, has smoke extraction been taken into consideration when it comes to that? And then also breathing apparatus, should somebody have to go into an area to extract somebody who's maybe become unconscious, it is suggested that breathing apparatus be near that active area. All right, with that, we're coming right to the end, and I'm just going to summarize very quickly. So what we've learned today, that lithium batteries are made up of many small batteries or cells, and they're housed in a plastic or in a metal container. Lithium, we've learned, is highly unstable, and we understand now why. And that's what makes the lithium ion. One of the electrons has moved off, and that has made that lithium atom very unstable. Thermal runaway is very difficult to stop. Lithium ion fires, we have learned, burn at very high temperatures. By using the fire triangle, we currently are able to cool these cells that are in a battery, or we can attempt to cool the cells that are in a battery. But we've also learned that we cannot extinguish a cell that's actually on fire, that's burning. That simply has to burn itself out. We need to bear in mind that extinguishment and containment of small, medium, and large fires is very, very different. There is no one solution which fits all. And then finally, we've learned that we need to understand the risks, particularly the secondary risks of VOC gases. And by understanding those, we will, I'm sure, develop ourselves a sound action plan. With that, I think I have spoken enough for one day. Bev, Danley, I thank you for the time, for all of you for listening. I do appreciate it. If there's anything that you feel you might need or I might have excluded, you are more than welcome to contact me. My email address is currently on the screen, and I am more than happy to answer questions if I can.
Thanks, Duncan. I've got a few questions in the chat.
Sure.
From Yassine, she wants to know whether overcharging a cell phone, what she said, when one overcharges the cell phone, can it catch fire? My kids always
the answer is yes.
Okay.
Yeah.
The next one, is it purely electrolytes? Sorry, the chats are coming in and moving my screen.
Sorry.
Is it
purely electrolytes that burn? No, it's the lithium that starts it. The lithium's the culprit. The electrolytes are added to it. Yeah.
Okay.
Which and together they cause a horrible fire.
Okay, next one is, what about poisonous gases while putting out fires?
Those are your VOCs. A serious concern, yes. Hydrogen fluoride is one of them. Hydrogen fluoride is deadly to us.
Okay, hybrid vehicles. Sorry, my screen keeps on moving. Hybrid vehicles, can they settle out while driving, and how far from the main residence should the vehicle be?
The answer is yes, they can catch a light while driving. Remember that most battery fires will take place when the battery is being charged. So while you're driving, often you're charging the battery at the same time. So yes, that can happen. How far from the residence? I don't know. Far enough away that it won't cause the house to burn down if the vehicle goes on fire.
Sorry.
So I was going to say, in most instances, though, the vehicles aren't parked far from the house; they're parked in the garage, which is part of the house.
Okay, Gert van Nel would like to know whether a Synergy lithium-ion battery storage system with an integrated internal fire suppression system would be able to extinguish itself, from your knowledge.
Yeah, I must admit I'm finding those products very interesting, because I still haven't been able to ascertain, and the manufacturers of the product aren't letting us know what the medium is that will extinguish this fire. So that's a very interesting one. Those products, so you have your battery, you have an inverter, you supposedly have this a suppressant medium, all in a very solid metal housing. So there's nothing you can do. You can't use a fire extinguisher. Everything's happening inside this metal. But I still am not able to find out what that extinguishing medium is. It's very interesting to know.
How fast can a cell phone battery go from fine to fire?
Well, I don't know of the actual timing, but once it goes into fire, a normal person wouldn't be able to go anywhere near it. I had one, funny enough, a real life example just the other day, and fortunately the cell phone was on a marble counter. If it had been on a bed, the bed would have been set alight. Most probably the house would have burnt down. On the marble counter, though, it burned for about 2.5 minutes. It's highly explosive and a frightening fire to see, and yet a very small battery. How quickly would it go? I don't know. I really don't know.
Thank you. Hydrogen fluoride is not an organic compound. What is the primary organic compound which burns?
I don't know. It's all generated from the electrolytes. I would have to check that up and get back to you.
Okay. Then final question from Fran Dreyer. How often are there lithium battery caused fires?
How often?
Yeah.
Gee, I'm a little bit out on my stats now, but if I remember correctly, I was reading an article on the New York Fire Department, and currently 60% of the fires that they have to attend to were caused by lithium-ion batteries.
There are no more questions, and I don't see any hands up, so I hand over to Denley now. Thank you, Duncan.
Great. Thanks so much,
pleasure.
Duncan. It was so informative, and we've had great reviews that it was really a great presentation. We really thank you. Just a reminder, it's 2 hours CPD. Bev will get those certificates through to you as soon as the IISA has approved them. And yes, thank you once again for attending our awesome webinars. Great. Have a great day.
Denley, thanks very much for having me, and everybody who listened. I do appreciate it very much. Thank you. Bye.
Cheers. Bye.
Thanks. Bye.